Okay, good. So the event that was seen at the time was the gravitational waves that had taken place very long time ago at a very far away place in the universe. And this was the merger of two objects whose existence had also been predicted soon after the the discovery of the general theory of relativity, which were called black holes. And here you had two black holes that were merging, and they had masses of 36 and 29 solar masses. Now, this may look like a large, very pretty heavy guys, but actually not all that heavy on the scale of the cosmos. But the main scale is that of one solar mass, which, as the name suggests, is one mass of the sun. But you see, 29 and 36 does not add up to 62. But the new black hole that was formed was of 62 solar masses. So you may be wondering, where did the three solar masses go into? The missing 36 plus 29, which gives you 65, but the new black hole was only 62. So what happened to the other three solar masses? Well, so that energy of three solar masses in a fraction of a second turned into gravitational energy, and that is how gravitational waves were formed, which then moved from the source where these black holes merged to all the corners of the universe. So this is the amazing thing. But now India will also join this project and will have its own node. It will be called Indigo. That will be the India-based LIGO observatory. And this happened because of a huge improvement in technology. But I'll try to show you. And then there was a Nobel Prize also in the next year to Kip Thorne and Rainer Weiss, Barry Barish, who were the pioneers of this experiment. But one must also mention the contributions of Jim Weber, who passed away already more than 30 years ago. He had tried to look for gravitational waves. So Albert Einstein, this is Albert Einstein seen as a young man. And then the black hole solution was found within a year of his general theory of relativity by this gentleman with a fine mustache called Schwarzschild, who found the solution within a year of the general theory of relativity, but one never heard of
Professor
him again.
Anant,
Yes. Yeah.
The slides aren't changing, so you're sharing the wrong screen.
Oh, I'm sharing the wrong screen. Okay.
No, you may have to yeah, now
It's okay now?
Yeah, now can you move to the next slide?
Yeah, I will. Okay.
Yeah.
Has it changed?
Yeah, that's what I was trying to leave a message for you, but you didn't probably see it.
Yeah. It doesn't open too many of these. Okay. So this person with this thick mustache called Schwarzschild, who found the solution named after himself, which essentially is a black hole solution. One didn't hear of him because he was in the front of in the First World War and caught some disease and passed away soon afterwards. So you see, in all these stories, you can see so many of the kind of the human aspect of scientific work. So here you are, the theory of relativity is announced in the middle of the First World War, and then there's a person who finds a solution. And 100 years, so Schwarzschild gave the solution to what is called a static black hole, which was generalized about 40 years later by Roy Patrick, who was a person from New Zealand working in England at that time. So you see the time scale in each of these scientific discoveries is the order of decades. And pictorially, this is what happened. There were two black holes which began spinning around each other. And then what happened is that they merged together. And in this gigantic coalescence of these two black holes, the entire fabric of space-time itself is shaken. And that is gravitational waves. And these are the signals that we're seeing in detectors in two different places in the US. One is in the western state of Washington, and the other is in the southeastern state of Louisiana, present in a place called Livingston. And then you can see what is essentially the ripples of space-time coming from that black hole merger over there. You can see that even though these two are separated by thousands of kilometers, each one of them saw essentially the same signal, but there's a slight delay between these two signals, which is to say that the shaking of the fabric of space-time took a little bit of time to travel from one place to the other. And this you can see, this is the Earth, this is the United States, that is the state of Louisiana, L1 over there, and this is H1, which is for the Sanford, which is in Washington, DC. And this is the principle of this laser interferometry, is to have laser beams which split. And this is sitting in the fabric of space-time. And when the fabric of space-time itself is shaken, then there'll be an interference phenomena between the various light sources that are bouncing off one another over there. So this principle was what was used by people like Kip Thorne and Rainer Weiss, and that's the reason why they were honored with the Nobel Prize, the three of them over there. It almost seems to be that you necessarily have to be bald in order to get the Nobel Prize, but there are some counterexamples also. So these are the three. And the point is that these are people who worked for decades. I mean, literally about 30, 40, 50 years, they had worked on this idea before they actually could see their work being demonstrated. Soon afterwards, so what we saw so far and discussed so far was about the merger of black holes. But there are other objects in the universe also, which are also very interesting animals in this cosmic zoo. And there are objects known as neutron stars, which are also present. They're not black holes, but they're neutron stars, as the name suggests. But soon afterwards, what happened was that the LIGO observatory started seeing even mergers of neutron stars. And in the neutron star environment, there's a lot of material present. Black holes, as the name suggests, are black. We don't know much about what goes on inside them. They are theoretical solutions. And literally, we don't have any information about what is inside the black hole. Therefore, these are very beautiful theoretical objects. In contrast, these objects, which are called neutron stars, which have matter in them, all kinds of matter. And then in the coalescence of neutron star, we can also see a whole lot of other things coming, which is not possible with black holes, but is possible with neutron stars. You can see light being emitted over there, and one can look at the various parts of the electromagnetic spectrum in the light, bright blue and X-rays and all kinds of radiation coming from the same cosmic event. And so this leads to a new field called multi-messenger astronomy, where you can see gravitational wave physics going hand in hand with conventional physics using satellites and other kinds of telescopes and so on. And this work, in order to honor it, there was a medal given to Bernard Schutz, a pioneer in this particular field. So if you want to ask what is the timeline of inquiry that goes on in physics these days, there's a pretty long timeline. It started at the black hole over here, at the Big Bang, I mean, which is called the Planck era, named after Max Planck, one of the great scientists of the late 19th century, the 20th century, Planck era. And then here the Big Bang took place. And then if you look at the scale over here, these are very small time scales. This is 10 to the power of minus 43 seconds. I've given this only to illustrate to you what are the kinds of scales that we have in physics today. So this is where we are today at this time slice over here. And we all came from this long history of the Big Bang, where matter was produced and radiation was produced and galaxies were born, so on and so forth. And this is where we are. So you're looking at things like 500,000 years, a billion years. All this sounds like fiction, but people who work in this field, they get used to these things and they have to get used to it. There is no chance. So that's the kind of time scales that I was talking about. But if you would rather think of what are the length scales in the universe, you could do that too. You know, for instance, here we have over here, where shall we start? We shall start over here. Here is a quark, which is a very, very, very small object, which is present inside a proton, which is in turn present inside a nucleus, which in turn is present in nuclei, which is present in atoms, and the atoms are present in molecules. So here you have an oxygen nucleus, and then here you have, a silicon molecule over here. Then there's a sand grain. There's a large number of sand grains over here. There's also a human footprint over here to give you what is the length scale. So here you can see the scales of very, very small lengths, whereas here is something that we are accustomed to, which is a meter, which is pretty large. Most of us have feet, which is of the order of like maybe 20 centimeters or so. This is the human footprint. And this is a beach that is on the Earth. And then the Earth is sitting over here, going around and around the sun over here. And here is probably Jupiter out here. And then we have the entire solar system, which sits in the Milky Way. And the Milky Way itself is a galaxy, which belongs to a cluster of galaxies. And the galaxies are all present in the visible universe. So you see here is the big picture today that we have over let's say, the 20th century, where we evolved a picture of what are the length scales and the time scales of the universe. Now remember that all this, whether it's the Big Bang Theory or galaxies, all these things have come into being only in the 20th century. And of course, now we know more in the 21st century also. Quantum mechanics was born in the 20th century. Astronomy was a few centuries earlier. I mean, astronomy as an aided astronomy with the telescope and many other optical instruments. While before that, let us say until the 1700s, it was only naked eye astronomy. Analogously, when you look at the microscale in biology and so on, it's the discovery of the microscope that allowed us to get a picture of in biology. I want to switch to another very remarkable discovery already, which is in the field that I work in. It's the discovery of what we call the Higgs particle. Now, everybody has heard about this, so I just thought that I would tell you a few words. There's also a lot of romance associated with the story, which also required a very large experiment to build in a very large laboratory, which is called CERN. This is the European acronym, the nuclear, for the Nuclear Research Center, European Nuclear Research Center, CERN, over here. As the name suggests, it's a European laboratory, which means that it requires a consortium of nations to participate. So here again, there's an idea and a notion that you must think about, that modern science today is done not just by individuals, but by members of society, by political institutions, political organizations, which come together to pursue science as we know it. And here were the words, and actually we watched this also on the computer already 8 years ago from the then director of CERN, Rolf Dieter Heuer. And he is this German person who says very few words. And all he had to say to the camera was, as a layman, I would say, I think we have it. Then he turns to the audience and asks, do you agree? Now, this was quite remarkable and like an anticlimax, but I think he did it with a purpose, which is to create excitement from the large crowd that had gathered in the auditorium at CERN. So this was a particle whose existence had been predicted by Peter Higgs in 1964. Already at the time, nearly 50 years. It took 50 years for the discovery of this particular particle. The reason is that the mass of the particle was not known, and it proved to be a rather heavy elementary particle. And in order to have enough energy under controlled conditions, it took a lot of effort to build this laboratory and to actually build the detectors and to have a search strategy and to find all this. This mechanism, there are multiple authors for this, but the particle got named after only one of them, namely Peter Higgs. And it took several generations of dedicated experiments to find this particle. So it required, again, just like in the case of LIGO, which required very sensitive and very advanced technology. Here, there was massive amounts of technology. There were superconducting magnets and control of beams and so much technology. And this was on that particular day where two of the persons who were involved in the discovery, standing over here, well, Peter Higgs has hairs, but he was still given the Nobel Prize despite having hair. Soon afterwards, this is the two of them. This is Francois Englert, and then this is Peter Higgs over here, and this is Rolf Dieter Heuer. Now, Francois Englert, you should know, and there's always a bit of history in all these things. He was a Jewish person from Belgium, and during the war, it's remarkable that he survived. I think he had to be hidden by other people who took care of him during the Second World War. So you see how much the history of all these subjects is also kind of embedded and enmeshed in the history of those regions. So to give you an idea about what LHC looks like, so this LHC is the name of the experiment. It's called the Large Hadron Collider. And this is what it looks like. And it has a circumference, it has two rings whose diameter, whose circumference is 27 kilometers. That's a pretty long distance, you know, and you must have a great deal of control. Protons are circulated in two of these rings, and then they are brought and collided in 4 locations, which are the names of the experiments, which is one of them is called the Compact Muon Solenoid, other is called Atlas Toroidal LHC apparatus. And then there are 2 other experiments. I can't say too much about this because then I'll never finish this talk. So, but this is to give you an idea of the scale of the experiment over here. The circumference is 27 kilometers, and it goes under 2 countries. It's under both France and Switzerland. And here is the Lake of Geneva over here. And you see how it's very deep under the rock to prevent contamination of the signals from cosmic rays and so on. So it's a phenomenal engineering feat that such an experiment could actually have taken place. So this is all the details about this particular experiment that I want to tell you about. It's an accelerator under 2 countries with the circumference. There's 7 detectors, and its goal is to test something that we call the standard model. So it's a theory of several interactions, namely the electromagnetic interaction with which we are all familiar, the weak interactions, which is known, which is familiar. For instance, it leads to the decay of radiocarbon. It's also used to produce medical isotopes. Those are the weak interactions. And the strong interactions which keep quarks together in strongly interacting matter like protons, so on. Then there are many, many other goals for the LHC. For instance, supposed to search for so-called dark matter, which holds the universe together by giving enough gravitational attraction. But none of these have been found yet by the LHC, maybe in the coming years. It also studies the nature of the Big Bang that we talked about earlier and the nature of the primordial plasma. So these are the many experiments over there, and India is also a member of one of them. It's a member of this compact muon solenoid experiment over here. And we also have people working from different institutes in this ALICE experiment, which is a large ion collider experiment. Many other experiments which I don't have to carry. Now, to give you an idea of what elementary particle physics detectors and experiments look like, I mean, here is a cutout of the CMS. I mean, and here is an average person standing over here, another average person walking away. Just look at the scale of this experiment. So what happens is that protons come along this line over here, this line, and collided at this place at very high energies. And of course, whatever results from this particular collision is produced, and you have to detect and see what is there. And one of the particles that you detected in such a collision was the Higgs. So that is the reason the number and the probability of actually producing a Higgs in such an event is very small. So you have to carry out large numbers of collisions before you can be sure that you have actually seen a Higgs. Here's a little bit of data to give you an idea of what kind of scales we are talking about in science today. The total weight of this CMS detector is 14,500 tons. I mean, what kind of an awesome weight is that? Sounds like the weight of a ship or something like this. But here what you're talking about is, you're talking about detectors and scientific equipment. And a lot of them, of course, are pieces of metal through which the collision products pass through. Nevertheless, this is what the weight is like. And this is the overall diameter. The other experiment, ATLAS, is actually even larger than this in its size, but not as heavy. So this is how the Higgs was produced, which was then seen. That is, these 2 protons which collided head-on, they are made up of constituents, large number of constituents, some of which are called gluons. And then these gluons collide through these virtual processes of producing certain particles in the intermediate states over here that is given in this triangle. And then the Higgs is produced and then decays into these 2 photons. And what the CMS detector sees are these 2 photons, from which it has to reconstruct the fact that a Higgs had been produced at some point. So you see what a complicated story this is. When we talk about a discovery, it's not just about having a petri dish and seeing something growing in that. In the last 100 years, science has changed so much that it's a cooperative effort, and what we call a discovery is not quite the same as seeing a comet out there or seeing penicillin growing in a petri dish. I hope some of these comments are making sense. Well, anyway, so at the press conference that Rolf Dieter Hoyer was speaking about, this is one of the graphs that was shown by one of the 2 people who presented the results, one of who is now the present director of CERN, Fabiola Gianotti. She was with the ATLAS collaboration, and there's Joe Incandela, who spoke for the CMS collaboration. And this is what he showed over here, the Higgs decaying to 2 photons. And this red line over here is what you would have seen in these number of events had there been no Higgs. So what we see over here is this small rise and fall in the number of events over here, from which we concluded that there must be a Higgs particle at the mass of 125 in what we call our GeV units for giga electron volts. On the scale, the proton weighs about 1 GeV. So you can see here's an elementary particle that is 125 times as heavy as 125 times as heavy as a proton. I'll just pause here for 1 second to see if there are any urgent questions and to see if the presentation and the recording have been quite decent. May I request Dr. Bitasta Das to say if everything's okay?
Yeah, it's going on well.
Okay.
The audio, everything is working.
Okay, good. Are there any urgent questions, or shall we move on and then maybe we can come back to questions later? Okay.
Is
Fine.
there any question? Maybe we can move on and we'll take the questions at the end.
Okay. So the keeping in view the title of this talk and also the series at which this talk is being given, it is only natural that we ask the question of what is the nature of scientific discovery? What exactly is it about? This is a question that everybody must ask themselves. In the examples that I have given so far, I have talked about areas which require massive teamwork and technology for fundamental discoveries. Is this always so that it can only be done at this scale? You have a consortium of nations and large numbers of people first coming and signing large numbers of memoranda of understanding? Or is there scope for doing other kinds of discoveries just as interesting, which require less manpower, less teamwork, and so on? Yes, of course there are. Even in this era, there have been many interesting and important discoveries. For instance, high temperature superconductors, which are constantly found. And then there is graphene, which is a new state of matter from carbon, which has very wonderful properties, which is today being deployed even in medicine because it has the ability to retain molecules and to be able to have precision delivery of drugs to various specific parts of the human body, for instance. There are other objects that have been found in condensed matter systems. Topological insulators is one of them. There are many tabletop experiments which can also be of great interest. But all that said, one must admit that great advances in technology and science can only be made. There's real perseverance and single-mindedness. And of course, at this point, we also have to ask the question, what is the role of the individual? I mean, where do I fit into all this? Am I just a small atom in this enormous gas of scientists? Or do I myself have a role? If so, what is the role that I should choose for myself? How do I contribute? So, of course, this is a question that is not easy to answer. And in this series, I hope that many, many others will come and shed light on these questions. But let us also take some examples and see what some protagonists have to say about the nature of their calling. What is the message of all this? I also want to say that many of these comments and some of these slides were prepared before this COVID era. In fact, the last time I gave this talk was on the 29th of February of this year. At that time, I just could not imagine that the world would be what it is today, where we are all essentially cut off from each other and we only link through these devices. I hardly see anybody when I go out onto the street. I've not seen my students in months. They haven't seen me. Probably they are happy, of course. But it is very hard for us to keep our feet on the ground and to concentrate in this particular strange period that we are in. But that said, we still have no choice but to go on and to keep working. As Randy Pausch said, you cannot choose the hand that has been dealt to you, but you can only choose the way you play it. And I don't mean this as a kind of flippant comment or as a comment just to cheer you up. It is a fact that all of us have to face that it may be 3 months or 6 months or a year before things will even come anywhere near normal. So let us all try to concentrate and keep working and do what we can in this COVID era. And I also would like to thank Dr. Bitasta Das for, not being discouraged by this COVID era and to start this initiative and let the, have the kickoff right in the heart of this period. So let me take some examples from mathematics. I had said that, I will have to resort to some examples with high school mathematics, because mathematics is still an area where you can actually explain to non-specialists and even a non-expert like me can talk about things because we do understand there's something very universal about it. Let me take an example from mathematics, which is a very famous example called Fermat's last theorem, So he wrote down in his notebook that he found that there were no whole number solutions for the equation x raised to the power of n plus y raised to the power of n, which is equal to z raised to the power of n, except when n equals 2. This, of course, all of us know. 3 squared plus 4 squared is equal to 5 squared. We know the case all the way from Pythagoras, from the earliest days, we know it. And it's known in all civilizations, even though this is attributed to Pythagoras. This is known in every civilization because this is a basis for computing land area. So there's nothing in the world which is more valuable than land, as we all know from real estate prices. So we all do know, and everybody appreciates, that you can get whole number solutions for the equation x squared plus y squared equals z squared, where x, y, and z are all whole numbers or integers. Now, the claim of Pierre Fermat was that you can never find x, y, and z so that x cubed plus y cubed plus z cubed is z cubed, or x to the power of 87 plus y to the power of 87 is z to the power of 87. And he claims in his book, which he annotated, he wrote a comment saying, I found a proof for this. It's true that he found a proof for 1 or 2 such cases, but for not all. His claim was that this theorem is true for all powers n, but I don't think anybody could have believed that he had a proof for this. And this was proved very recently. It was only proved at the end of the 20th century by this person, Andrew Wiles. And Andrew Wiles claimed that it was his childhood dream to prove this theorem. And he is a very famous number theorist already by that time, but he had not worked on Fermat's last theorem. So it so happened that about 1989 or 90, somebody told him about a new result, which said that Fermat's theorem would follow if some other conjecture associated with 2 Japanese mathematicians, Taniyama and Shimura, was proved to be true. That if this particular conjecture of these 2 persons, who made this conjecture in the most terrible of conditions soon after the World War, they describe a time when there was no food available in Japan, and yet these 2 people used to discuss mathematics, and they came up with a conjecture at that time, and it took another 50 years for it to be proved, and this was proved by Andrew Wiles. So his task was reduced to proving the conjecture of Taniyama and Shimura, and there are 2 very beautiful books written about this, Amir Adsel and Simon Singh, on this particular. It's almost like a detective story that is worth reading. So Andrew Wiles actually proved this conjecture of Taniyama and Shimura. There's also a very beautiful BBC interview where he talks about how he had a certain Eureka moment when he saw that his proof was correct. He first announced a proof which had a flaw in it, and then it took him some time to fix that particular flaw. He talks about how that particular moment he saw how to break through the impasse. So you see, mathematics is an example where you can describe the problem and mathematicians can talk about their experiences also. So for those of you, especially the younger people who want to see what the enterprise of science is about, it'd be very nice to watch this BBC interview. There's another example from mathematics, and this is an example which derives part of it. Hello? 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 Have I lost anybody? Hello?
No, it's fine. You continue. Somebody's mic was on, so.
Oh, I see. I thought I had lost my connection.
No.
Yeah. So there's another example from mathematics where part of the results came from physics, and this is really a romantic story. So this is a problem that was posed by Henri Poincaré, I think in the year 1900 or so, and it took more than 100 years to prove this particular conjecture of Poincaré in 3 dimensions. And this was solved by this person whose photograph is very hard to find because he's a very reclusive person. So there are practically no pictures of his available anywhere in the world. He's like the Yeti. So any picture of his or a sighting is considered so rare that it's enough to be posted in mathematics. So he was working in St. Petersburg or Leningrad, and he used ideas developed by an American mathematician, Richard Hamilton. The ideas came from the physics world. So what Perelman did was he was able to prove and introduce some notions and prove this theorem, and he just posted it on the internet and then disappeared from mathematics. And he also refused what is considered the highest honor in mathematics, which is the Fields Medal, awarded to mathematicians below the age of 40 at the time when the award is made. And he also declined a $1 million prize due to the Clay Mathematics Foundation, which has announced 7 projects. And if you settle any of them, that they would pay you $1 million. And the only one which has been solved out of those 7 to date is, in fact, this Poincare conjecture. And Perelman actually refused to accept that prize. So you see, you need all kinds of people in mathematics and physics. Some very strange. Those are not interested in money. They're not interested in anything except truth. In a sense, as far as Perelman was concerned, he was interested in the question of the truth, whether it was the Poincare conjecture was true or not, and he was able to prove that it is true. And then he bid goodbye and walked away from it all. So here is another story. I think somebody else is doodling some blue marks in this. I wish people didn't do that. I want to introduce here a bunch of examples from theoretical computer science, which is, as the name suggests, is from computer science, but actually for all practical purposes, there's no difference between theoretical computer science and mathematics. And this has to do with drawing pictures and so on, most of them. And there's also a connection to us. And that is the reason why I think that it is important to keep this in mind and to read about how these things happen. So here is there are about 5 problems that I have listed over here, most of which have been solved in the last, I would say, 4 or 5 years. So here is a very active field in which there are small groups of people who work. They take up important problems and then go after them, with some kind of a sledgehammer, taking, tools from various other branches of computer science and mathematics, and then finally nailing the problem in such a way that, that it really paves the path for the future or developments in that particular field. So let me go over them. It's all pictures, it's all words and anecdotes. So this doesn't even require high school mathematics because theoretical computer science is not taught in the high school. So here are 2 graphs that anybody can understand. So let us take 2 graphs, G and H. And to the naked eye, they look quite different. And the question was, are these 2 graphs really the same in the sense that they are isomorphic? Isomorphic means what? The same form, morphism, to morph from one to another object. Morphology, all this just means that are they really the same? Iso being the same. So the question is, are these 2 graphs G and H the same or not? So here is an explicit map. A is mapped onto 1 over here, and then B here is mapped onto 6 over here, and so on. So here is a simple example where you have a small number of nodes and a small number of links that link various nodes over here. You can explicitly see that they are the same. The question is, if you're given graphs of great complexity with a large number of nodes and a large number of interconnections, can you or can you not decide whether they are the same? Of course, if you have an infinitely powerful computer with infinite amount of memory and infinite time at your disposal, you can take the first graph and keep, deforming it until you get the other one, or until you have exhausted all possibilities. And then you have an answer one way or the other that the first graph is isomorphic to the second graph or it is not. But that is not so interesting. We want to know whether in real life problems you can actually demonstrate isomorphism of 2 graphs in a reasonable period of time or not. And this question was looked at by many, many people. And here is this person who's one of the granddaddies of the field, Laszlo Babai. I think he works across in Chicago. So, so he wanted to ask a question whether these graphs which look different had the same underlying connectivity or not. And the phrase that is used in computer science is whether the algorithm that you have constructed is polynomial in time, as in the number of iterations you have to do in order to get the result that you like, or whether it is a quasi-polynomial, or whether it is exponential in time. Today is one day in my life when I don't have to explain the word exponential to anybody. Thanks to COVID, We all know what exponential is, and we are all scared to death of exponential time. It represents to the human mind an uncontrolled growth. So here, so if you had exponential time that is needed to decide whether two graphs are isomorphic or not, you would say that that is not a happy state of affairs. It's really going to take a hell of a lot of time to figure that out. So it was necessary to prove that this, or rather, it had to be settled one way or another, whether it is polynomial in time or quasi-polynomial in time. And then here is a very romantic story of how Babai announced a proof, and then he himself found a problem, and then he himself fixed this. So this is a simple problem that I thought would illustrate the kinds of problems that go on in some of the fields. Then there's another problem in computer science that they call Boolean circuits. Boole here refers to George Boole, who introduced in the 18th century a new algebraic system that's named after him. That's why it is called Boolean logic and Boolean systems. So this is based on binary logic, either something is on or off, zeros and ones. So there's something called the sensitivity conjecture, which had been hanging around for a long time, whether certain kinds of computer circuits, how can one analyze them? And here's a young man, Hao Huang, who was working on this problem, a very young person, probably not even 30 years of age, and how he took this problem and then how he mapped it. I think part of the work had been done by others also, and it had been related to a problem in basically in solid geometry of having cubes, the different corners of the cubes and coloring cubes, and to objects in mathematics that all of us are accustomed to called matrices. And then he talked about how he was able to settle this problem merely by looking at it. And I think he wrote a 2-page paper, which was a very elementary proof on solving this extraordinarily important problem. And this is something else. Again, these all look like beautiful geometric patterns. It looks like some of the kolam and rangoli that we do outside our doorsteps over here, with a certain number of links and a certain number of corners over here. So the question that mathematicians posed with a graph of this kind was whether you can have elementary building blocks and just move them around and link them and so on, have small subunits with which you can produce an entire so-called Ringel graph named after the author of this problem, whether a Ringel graph could be produced by using elementary objects which were called trees, and whether you can use a tree and have simple operations to produce an entire graph like this, whether you can have basic building blocks for such graphs or not. So this was settled, I would say, about a year and a half ago, and this was only an existence proof. It did not mean that given a graph, you would be able to find such building blocks. It merely says that there always exists a building block, which they call things, which tells you how to do this kind of operation by which you can actually cover it. So here is, again, a problem in graph theory. This is also of interest to me and some of my students because we also work on Feynman diagrams and Feynman graphs. And we have an interest in this subject also, though we find that most of the language used in this field in theoretical books are not very accessible to us, but we do have an interest in the subject. So these three people from 3 different places in 3 different countries together, you see, the modern era people also have a very wonderful way of collaborating through the internet by exchanging notes, having GitHub pages and having all kinds of shared resources, so that you can solve problems that 25 years ago or 30 years ago you'd have considered impossible. Imagine you have a small theorem, and then you write a postcard and you mail it to some other country, and then you've forgotten to affix enough stamps, and then it gets returned to you, and then there's a delay of 3 months. Just imagine the world that we are living in today, where you're up in India today, you work out a step, you send it to your collaborator in Argentina, and by the time you've gone to bed, he or she has started reading, worked out the next theorem, and then sends it back to you, and then build the next module. So the era in which we live is also one in which there's been an exponential rise in efficiency and creativity, at least I think so. So here is a problem that I thought that I would present to you as something that you can think about. So this is the connection that I wanted to tell you about, which feeds into the next project. Now, it is very difficult for scientists to acknowledge that somebody is actually better than them. So this is a general problem, because I'm so great and I have worked so hard and I have fought at the frontier of science and of human knowledge that nobody could have done it better than me. I'm a hero in my own mind. But all these come kind of crashing down when you're confronted with this personality called Srinivasa Ramanujan. He is such an amazing person who was dead at the age of 31 or 32. How much he could squeeze into those few years of creative life, and how amazing some of his ideas were. So there were many things today which are named after him. For instance, this object that I show for you here called the Ramanujan Graph. He never got up and said, today I'm going to write down the Ramanujan Graph. He didn't do that. Basically, in his work and in his notes, he always had some ideas which were discovered 40, 50, 60 years after he had written it down. And somebody found them to be so incredible that they named it after him. So it's in the sense that, you know, you have Euclid, many things are named after Euclid, or many other things which are named after great personalities. This was the effect of Ramanujan, that his discoveries and contributions were just so phenomenal. So here is something that's called the Ramanujan Graph by the authors of these three people, one of them Nikhil Srivastava and two other guys, Marcus and Spielmann, who together solved a problem, I would say probably about 10 years ago. This person, Nikhil Srivastava, I think he was in Microsoft in Bangalore at that time. So they solved this problem, which is called the Cadison-Singer problem, which arose in quantum mechanics as a problem, and then it got turned into a problem in linear algebra and graph theory and so on. And that is where the notion of Ramanujan graphs also come in. This is a very difficult problem to describe. It has to do with something they call network sparsification, which also has implications to computer algorithms and efficiency and so on. And they actually have used these objects called the Ramanujan graphs to solve what they did over there. So you think we are done with Ramanujan? I mean, this is the year 2020, and I think this would be the 100th year after his death. So how could he possibly have anything to do with us anymore? He's already been dead for 100 years. Well, one of the papers that I wrote with three of my students also is named after Ramanujan. It's called Ramanujan's master formula. We wrote a paper last year in mathematics. So he's not quite dead. Let me show you one more example over here. This is a problem that was solved a few months ago, which again derives its inspiration partly from this object called the Ramanujan Approximant. And what you have over here is a page from one of where he didn't call it the Ramanujan Approximant, of course. He was interested in knowing for irrational numbers what is the best way of expressing or coming as close as possible to the true value of an irrational number in terms of a numerator and a denominator. We all say pi is 22/7. Well, that's also a rational approximant. It's not a very good approximant. You can do better than that. So it's not just pi, but many other irrational numbers that he could talk about. So here are two persons, Koukouloupolis and Maynard, who settled something called the Duffin-Schaeffer conjecture on how to write down rational approximants to certain irrational numbers. And they were also motivated by the work of Ramanujan. In fact, actually, you can read a lot about these things from Quanta magazine on the net, which is an incredible resource. The people who write for Quanta, they really research a subject and express things very well. So I must also acknowledge their contribution to my life over here, at least as far as this talk is concerned. How are we doing for time? Very badly. So let me see. Let us see how discoveries in a changing world take place. Let me also talk about some more examples on high school mathematics over here. Here's an incredible discovery already about probably 10 years ago. Here is, at the time, little known mathematician originally from China working in the US. He announced a solution towards something called the twin prime conjecture. What are twin primes? Well, 3 and 5 are twin primes. 11 and 13 are twin primes. 19 and 21 are twin primes. Now, what do you people think? How many such twin primes are there? Well, the conjecture is that there's an infinite number of those, and we don't know for sure whether it is true or it is not true. There may also be primes which differ by 5. There may be primes which differ by 7. No, sorry, they can't. It has to be an even number. There may be primes that differ by 4 or primes that differ by 6. So, how does this go? So for a long time, and this problem is as old as antiquity itself, the first solution towards this came out of the blue from Yitang Zhang. And later, Terry Tao, who's one of the most powerful mathematicians today, most influential, he started a worldwide collaboration on the internet, and he crowdsourced problems to find improvements on the result of Yitang Zhang. So you see how the internet, which of course was born in CERN, today serves all the needs of research, and it can be used in a very creative way by individuals. It does not have to be done institutionally. So there are examples of people who have done this, and some other results came out which improved this result of Yitang Zhang. So now let us go and ask ourselves, what kind of Eureka moments take place in science? Are we the first to have asked this question? I had mentioned that Andrew Wiles had talked about his Eureka moment. Howe had also talked about his Eureka moment. Many others, probably Laszlo Babai, the way in which he corrected his proof, he must have also had a Eureka moment. So here's a picture of Henri Poincaré, who I had already shown earlier, who was described by E.T. Bell as the last universalist. So he describes his own Eureka moment about how he was working on a particular problem for a very long time, and how the idea flashed on him once when he just stepped off a bus. He suddenly saw what the solution was. This is to say that the human mind works in this way, that it tries to piece together things, and sometimes you just have to sleep on it to figure out how you get an answer. All of us have read in school about how Auguste Kekulé, who figured out the structure of benzene, so he saw a snake eating its own tail. So that is a very romantic story of how he saw the cyclical structure of benzene. So it is true that scientists, of course, work very hard for this moment, which may or may not come, one can't say. So let's see what some others have said about their Eureka moments and how they reflect upon the discovery that they have made after they have made their discovery and after they have found out how important their discoveries are. So Max Planck, on the discovery of quantum mechanics, this is what he says: the outside world is something independent from man, sometimes absolute, and the quest for the laws which apply to this absolute, he says, appeared to me as the most sublime pursuit in life. There are others also who have thought about this question about the psychology of creativity. What is it that makes you want to think about these things? In the 19th century, there were Jacques Adama and Hermann von Helmholtz, who talked about how it is that scientific discoveries and inventions can take place. So they think that there are some stages before you can actually say that something is a great discovery. So they organize this as preparation and incubation. You have to sit on the idea, and then finally, of course, you get the answer, and that is illumination. And eventually, of course, you have to check what you're talking about. So that is called verification. Now, Jacques Adama was one of the people who proved a very important theorem, which is called the prime number theorem, which had been proposed by Carl Friedrich Gauss, but Gauss couldn't prove it, and Adama was one of the two people who actually proved it. And this prime number theorem is something that is so compelling that every few years somebody finds a new proof for it. And I just read a few weeks ago a new proof was found for it. So you see, by the process of verification and proving, also the subject also moves forward. So there are various examples that they talked about. So when it came to Planck himself, the way in which he put things together, he had to, all of us know about the quantum theory. It controls all of us, right from the smartphone. Everything is quantum these days. So it combines a formula of two different people in two different regimes for electromagnetic radiation, for Planck's radiation, one due to Wien and Rayleigh. So he found a formula, but he didn't know where the formula came from. Kind of stitched these two things together. But within 2 months, he made a revolutionary deduction of his formula, that he found the fundamental theory from which he could get his formula. So that is where this whole thing of preparation and incubation comes from. That's a picture of Max Planck about how he had to abandon classical physics once and for all and introduce a whole new theory, which is something that happens very rarely. It's truly a revolution, that there is something called a quantum of energy, which we call Planck's constant of action today, and we get limits from there. What do others have to say about the psychology of creativity and discovery? Here's a picture of Subramanian Chandrasekhar, who has also spent a little bit of time talking about this. I'm also quoting Einstein over here. Since this picture was already there on slide number 3, I'm not putting it up again. So this is what Einstein says about how he got his theory of the equivalence principle, basically, the cornerstone of the general theory of relativity. So he says, I was sitting in a chair in the patent office at Bern. Actually, it's a bit of a surprise because most of the time he was standing in the patent office. Anyway, so he was sitting in a chair when all of a sudden a thought occurred to me. If a person falls freely, he will not feel his own weight. I was startled. This simple thought made a deep impression on me. It impelled me towards a theory of gravitation, says Albert Einstein. What does Chandrasekhar say? Now you see, Chandrasekhar is also a person who worked on relativity and had also been in close contact with many of these people. So he comes from a generation which is a little after that of Albert Einstein. He was born, I think, in the year 1917. So you can see that the general theory of relativity was 1915. So Chandrasekhar was born 1917, and then you can see that he took the subject forward. Some of the greatest textbooks in relativity are written by Chandrasekhar, Mathematical Theory of Black Holes, for instance. So he says, in some way, any new fact or insight that I may have found has seemed to me as a discovery of mine, but rather something that had always been there and that I had chance to pick up. Now, this is kind of a humble kind of comment, because it requires the human mind to step in and to recognize this. It also requires a lot of preparation and a lot of understanding to be able to say this. Actually, this question is there in all of science, and even more so in mathematics, whether something exists before you have found it or doesn't it exist. What does it mean to say that something is there? Is it a construction of the human mind, or is it really objectively there? I think it is all there objectively. Anyway, that's my opinion. So here is a picture of all these great people from that era, roughly. So you can see Albert Einstein sitting right here in the middle. There's Lorentz. Here is a sole woman in this picture, who is Marie Curie over here. So at this point, most of the things that I've talked about has had to do with men. In fact, that's the reason why I kind of introduced this picture at the stage, to show how marginalized women have been in this scientific enterprise. But of course, things have changed from this time, which was more than 100 years ago. So I'll talk to you a little bit about that too. So here is one of my colleagues from the Department of Physics at IISc, who asks the question, what is the nature of calling of a scientist? So he says, and this represents a kind of loneliness that some of us experience on a daily basis. So we cannot share our intellectual excitement even with our spouses or our closest friends. We are perpetually estranged from our fellow human beings. A good scientist, of course, has personal moments of intellectual triumph, but is forever denied those thrills which a triumphant musician standing in front of a stage feels the whole universe, or when the whole audience bursts into applause. In popular stories, scientists are very often depicted as awkward individuals, unsuited to everyday life, people who boil clocks for breakfast and keep on doing calculations on sand even when their lives are in immediate danger. I guess he's talking about Archimedes here. If all scientists were really like this, then they would probably have been eliminated from society by the process of natural selection. However, I believe that these popular stories tell us one truth. The fact that science is a very strange enterprise, although scientists themselves may not necessarily be strange people. So this is an article that he published when he was a PhD student 35 years ago. You see how prescient he was already at that time. More recently, this is what Nikhil Srivastava says. He does not believe in being a mega workaholic. This is what he said in interviews. I thought it'd be very nice to quote somebody who's rather young, because he's also evidently on the forefront. I don't know him personally. He's just a person I know from the media. Instead, he concentrates on having short spurts of focused, high-quality work. For example, even though he loves mathematics, he does not feel it's imperative for him to be doing math all the time. Rather, he finds more productivity in deeply thinking about one problem for weeks or months, and also taking time off. He also says you should fail in different ways. This is very important for students who are here, if there are any students. You should fail in different ways, but if you know you have tried everything and you're still failing in the same way, you may have to give up and move to another problem. Now, all the examples that I've talked about are, in a sense, representative, but they are not exclusive just to mathematics or physics or computer science, even though I have derived my examples from there. I, of course, mentioned Alexander Fleming and penicillin, this is biology. There's, of course, phenomenal discoveries in many other fields. Theory of evolution is one of the very great achievements of mankind. Mendel's theory of genetics, how did he figure out? Now, this is at a time when one did not know the underlying, genetic makeup of human beings or living beings. DNA and all these things were unheard of. And yet, Gregor Mendel came up with this theory of genetics long before we knew the microscopic basis of inheritance. So to me, that is another phenomenal discovery. But, as with many of these things, many people have written papers after his work, suggesting that perhaps he manipulated data. Doesn't matter. We cannot judge the science of a 19th century person with the knowledge and experience of the 20th or 21st century. Let us give these great people their due. I think this is a phenomenal achievement. Then there was also the whole theory of the continental drift. Now imagine what kind of a person could come up with such an idea that continents can drift. I think the person who proposed this is a Swiss geologist. I think probably nobody took him seriously during his lifetime. I'm not sure he was Swiss. Anyway, whoever. Then there were other people who had theory of ice ages. This was long before we had radiocarbon dating and, knowing and to pull out ice from, let us say, various deposits in Greenland or Antarctica, to know and to objectively prove that there were ice ages. Just based on gross phenomena, people were able to discover that ice ages must have existed. Imagine Louis Pasteur, a theory of microbes. Person says that both diseases and beer and yogurt all have the same underlying basis. Based on what? Just think of the phenomenal achievement over there of the Pasteur's theory. Or you can think of Shannon's information theory. And the whole enterprise of biology, here is a book called The Eighth Day of Creation. It's already a bit old. It was written probably in the 1980s. Looked into biology. Biology is a field in which there's been explosive growth. So, but still, you can have a look at this book if you're interested. I have quoted for you Chandrasekhar and Planck and Henri Poincaré and all these people. But what do biologists have to say about the world and science and their enterprise? Well, here is Charles Darwin on his theory. So he says there is a grandeur in this view of life, with its several powers having been originally breathed into a few forms or into one, and that whilst this planet has gone cycling on according to the fixed law of gravity, from so simple a beginning, endless forms, more beautiful and more wonderful, have been and are still being evolved. You see his entire view towards nature. Here is an example of science and mathematics done by women that I said it is necessary for us to mention, and you also are yet to answer the question as to who was on the slide number 2. Well, there's Ada Lovelace, born the Byron, That was her birth name of the great poet. And she is today considered as the founder of modern computer science. Then you have Emmy Noether, who is considered founder of modern algebra, whose work is at the basis of understanding field theory. Then Marie Curie, who was born Maria Sklodowska, that was her birth name, and discovery of radium. Cecilia Payne, so this is the answer to the quiz. She's the person who figured out the stuff that the universe is made up of. Then in mathematics, there's Julia Robinson, who found the solution to Hilbert's 10th problem. Hilbert I had mentioned. So in the year 1900, at the first International Conference of Congress of Mathematicians, Hilbert gave 23 problems. He gave a list of 23 problems, which he said that if you solve this, it will really break open the path to developments in mathematics. So Julia Robinson, along with some others, showed that solution to certain Diophantine solutions. Diophantus was a Greek mathematician, which concerns solutions in rational numbers, that it is undecidable. This was a breakthrough proof from Julia Robinson. And dark matter, which I had mentioned a little while earlier, the stuff that keeps the universe together, its existence was inferred by Vera Rubin, who passed away a year or two ago. The pulsar was discovered by Jocelyn Bell, as you all know, for which she was not awarded the Nobel Prize. And then, of course, you know the work of Rosalind Franklin and the path to the double helix, fundamental work. And of course, it's very controversial. And you know that the first woman Fields medalist was only this recent in the year 2014, was awarded to Miriam Mirzakhani from Iran, who was working in the US. But as with most of these people whom the gods love die young, passed away already a couple of years ago. You know that there's an upper bound of the age of 40 in the year 2014. And if she passed away already, she couldn't have been more than 46. So tragic. And CERN today has its first woman director general, Fabiola Gianotti. So these are the pictures of some of these people, how they have evolved over the years. This is Emmy Noether, this is Mirzakhani, and this is Gianotti. What about science in our country? Everything that we have talked about seems to have to do with another time and another place. Well, of course, India's science has been going on all the time. People do know that for well over 100 years, science has been growing. Already mentioned the examples of Ramanujan and his fantastic mathematics, which is alive to this day, Raman and his effect, Saha and his equation, Bose and his statistics, Bhabha and his interests, Rai Chaudhary and his equation, G.N. Ramachandran, who used to be in IISc for some time, and the triple helix. There's Birbal Sani and paleobotany, and there's Janaki Ammal and cytogenetics. There are many books, but as it happens, I think not enough is known about what goes on in science in India. So one of the aims of this series, I hope, is that many, many more people will come forward and talk about how they do science. So science in India into the present has completely changed, in my opinion, with science emerging as a profession. We have international standards, of course. We provide a lot of opportunities for the present generations. And what is missing, in my opinion, is not many people talk about how they go about their work. It would be important to explore this in detail. About 15 or maybe already 20 years ago in IIT Kanpur, Manindra Agarwal and 2 of his students had settled a very important problem, but they have talked about how they went around solving that problem. It's a very nice story. One of my very senior distinguished colleagues, Anil Kumar, he has talked about his own discovery of the nuclear Overhauser effect in biological molecules. He has written some very nice articles about all the trials and tribulations that he had to go through in order to make his discoveries. So an example of science in the 21st century. So here we have Venki Ramakrishnan, who talks about his ribosome discoveries and so on. So he makes a comment, which I think is important to keep in mind, that it takes courage to tackle very hard problems. And yet he says that it should not be turned into a contest. He has all these warnings, which are very good. And he has also emphasized the importance of multidisciplinary training and taking ideas from many fields and the importance of hard work. This is not what he said, but this was Seneca the Younger. Nobody knows for sure whether he said this or not. So this all hangs together, that in order to be lucky, you have to be very well prepared. And the saying is that luck is what happens when preparation meets opportunity. But why should we do science at all? So here is something that is answered partly by Robert Wilson, who was the director of the Fermi Lab. So he says, and he had to give support one of his projects in the US Congress. And he says only from when asked if basic science has anything to do with defense or has any defense applications, he says only from a long range point of view of a developing technology. Otherwise, it has to do with, are we good painters, good sculptors, great poets? I mean, all the things that we really venerate and honor in this country and are patriotic about. In that sense, this new knowledge has all to do with honor in country, but it has nothing to do directly with defending our country except to make it worth defending. The reason I'm saying this is that, you know, policymakers and others have to have a perspective on all these things. They can't just be hacks and bean counters. They must know the history of their own country. They must know about funding agencies. They must know how to answer the elected representatives of the country also when questioned. Victor Weisskopf, who was one of the early directors of CERN, has this to say: the value of fundamental research does not lie only in the ideas it produces. If science is highly regarded and the importance of being concerned with the most up-to-date problems of fundamental research is recognized, then a spiritual climate is created which influences all other activities. An atmosphere of creativity is established which penetrates to every cultural frontier. Applied sciences and technology are forced to adjust themselves to the highest intellectual standards which are determined in pure research. That is what attracts productive people and brings productive scientists to those countries where science is at its highest level. This is something to be kept in mind. So let me just conclude. I should not lose an opportunity to preach. So my advice for young people who I hope are in this audience, just follow your hearts. Nothing is more fun than research and discovery. And this will throw open the doors to a new tomorrow. Of course, it requires a lot of patience, like running or sprinting a marathon. You know, Thomas Alva Edison described genius as 99% perspiration and 1% inspiration. I would put it more like 99.9% and 0.1, but anyway, nobody asked me for my opinion. See also this famous speech given by Richard Hamming, which is called You and Your Research. So let me finish again with a quote from Subramanian Chandrasekhar, where he says, the pursuit of science has often been compared to the scaling of mountains. High and not necessarily the highest, but who amongst us can hope, even in imagination, to scale the Everest and reach its summit when the sky is blue and the air is still, and in the stillness of the air survey the entire Himalayan range, the dazzling white of snow stretching to infinity? None of us can, I'm not able to see this word, can hope for a comparable vision of nature and of the universe around us. But there is nothing mean or lowly in standing in the valley below and awaiting the sun to rise over the Kanchenjunga. I'd also like to thank some of my colleagues for Daniel Wheeler. And let me finish with this epitaph of David Hilbert, who said in German, Wir müssen wissen, wir werden wissen. We must know, we will know. So let me stop here and thank you for your patience and attention.
Thank you, Professor Ananthanarayan, for this elaborate and detailed lecture. We have been, introduced to many things that we didn't know, and we have a little time left for question and answers. Shall I take around 5 questions?
Yes, of course,
yeah.
Of course. Yeah.
So I also wanted to tell to the participants that this series or this series of events is called Paraspar. That means we would like to have an exchange, and the questions need not be typically scientific questions or science questions. Even non-science background can have questions that one might think are basic, but we welcome them and we'll try to address them as much as possible. So I'll take the first question. This is somebody called Megha who was asking, what are topological insulators?
This I really cannot answer. It's a particular class of materials that is found in the laboratory. They have they have properties associated with certain conservation laws which are associated with the with the topology. Topology is a subject again which was defined by Henri Poincaré, who I mentioned, which talks about shapes and how you can deform shapes and how can seemingly deformed shapes be considered equivalent. So Poincaré was interested in the classification of such objects. A well-known example being a donut and a coffee cup are topologically equivalent. Now, in the laboratory now, they fabricate materials which are called topological insulators. And I'm sorry, I really cannot answer this question very well, but my colleague Dityaman Sen is a world expert on these things. Sorry, I can't really say.
Okay,
they say, yeah.
Yeah, next question.
You can hear me, no?
Yeah, we can hear you.
Yeah.
We can hear you. The next question, how were photons produced due to Higgs different from those generated due to other modes?
No, I don't understand the question. Could you please repeat?
Yeah, one second. There's somebody called Ramakant Joshi has asked this question. How were photons produced due to Higgs different from those generated due to other modes?
No, they are not different. The thing is that you can only observe a particle that may have been produced by looking at its decay products. So these are the photons that are the usual photons. And the way in which I was talking about discoveries earlier was that you must have a hypothesis testing, that you have a specific kinds of photons that your detector has seen. And then you have to infer from that they were born in the decay of a Higgs. That's the only way to answer this question. They are not different from any other photon. See, the Higgs is also belongs to the standard model. So all the particles that it interacts with are standard model particles also. Oh, I see the questions now. Okay, yeah.
Okay, I'll just read out the next question.
Yeah.
How QCD helps in multi-messenger astronomy?
It does not. Multi-messenger astronomy today is an emergent field where when neutron stars merge, they produce a lot of new matter, various kinds of nuclei and so on. And the processes which produce all these nuclei and matter over there, they emit radiation during the process of their formation. And these other detectors like satellite-borne or balloon-borne instruments simultaneously see the signals coming from the same catastrophic event. So that is what I mean to say. Yeah.
That question was from Sandramoli Sandra, and I'll read the next question.
Okay.
The next question is by Raj. Nowadays, we have so many high-tech app facilities, but still research nowadays have become like a corporate work, and this is quite contradictory to the good olden days of research with less facilities. Is this due to digital dementia among youth? Could you please elaborate on this?
No, it's a very good question. Of course, time and tide wait for no man and no woman. So the world is a very rapidly changing place, and we cannot be romantic and say that things have to be as they used to be. You know, it was in the 19th century, you had Lord Kelvin or Lord Rayleigh or Lord Rumsford who did this or that. In the modern era, it's a profession, a very rapidly moving and competitive profession, and it requires all these technological inputs. The same thing you can say about mathematics. You know, Chinese people did it with an abacus. Why do we have to go to supercomputers? So science also has to adapt to all these changing factors in the real around us. Have I answered the question?
Yeah, maybe because of the lack of time, we'll go ahead to the next question. I'm sure you have answered this question.
Oh yeah.
This is somebody by Anita Dayanand. Is the process of formation of Higgs, in the process of formation of Higgs, why will it decay into protons?
You see, whenever there are particles which have interactions with other particles, if the mother particle is very heavy and it has interactions with lighter particles, it will invariably decay into the lighter particles. It cannot be prevented. That is just the nature of the game. Just like if you have particles with strange quarks in them that are formed, let us say, in cosmic ray collisions with the Earth's atmosphere, the strange quark is heavier than other quarks, and therefore it will necessarily decay into these particles. That's the as the nature of the game dictated by the special theory of relativity, that the mass of a particle, if it exceeds that of other lighter particles, sooner or later through interactions, it will decay into the lightest particles. Okay, that is allowed by the theory.
The next question is from Sansari Viswas. I am doing masters in cosmology. I am doing masters in cosmology. I want to know how is a daily life of a theoretical physicist.
Daily life of theoretical physicist. Well, you get up in the morning and I guess you have to chat with your friends on Facebook. That's of course a given. I mean, the daily life of a theoretical physicist is one where he or she is thinking about a particular problem, is trying to extend the techniques that are needed to attack that particular problem, find a new formula where you were stuck the previous day. So this is the kind of thing. It of course varies from field to field, and now many fields are very heavily computational. You have to debug your program, and yesterday the program had crashed, so today you have to correct it and run it again. You have to validate your code and make sure that it gives an answer that makes sense. So for a cosmologist, I suppose these days they do massive simulations on computers, how galaxies are formed, how do you test a particular picture of dark matter, is it valid or it is not valid. Recently there was a discovery from the Indian Institute of Astrophysics about the lithium content in stars. So a theoretical astrophysicist working in this field would be looking at plots of lithium concentrations in various stars. He or she would be comparing their formula with that particular data that has just arrived. So I hope that this answers your question.
The next question is from Pooja Chitre. How do we inculcate scientific temper in us? Our schools and colleges focus more on exams and marks these days. The importance of cultivating scientific temper and love for research is not is lost.
So I guess that this is a very India-centric question, because it is something that we have to deal with. There's nothing much we can do about it. I think, as with most other challenges in life, is you have to just do your best and hope that by setting an example that we will be able to inspire others and just do our best and produce the best possible results that our work can do, and just take it up from there. It may sound a bit pessimistic, like I'm offering a thesis that we are just doing our dharma and so on. But I think we go beyond that. For instance, the fact that we are engaging today, that I as a speaker, Dr. Das as an organizer, and you as a student, you're present here and you're asking this question, is all part of that process and symbiosis which will take our society forward. Beyond that, what can I say?
May I request everyone to mute, please? Okay, the next question is by Vishnu. Where can I look for books and other resources to find out about the way things were discovered, the thought process, designing, experiment, etc.? The kinds of references that I have given, it has come through long years of collecting all these sources. I can't quite say how to do these things, but if you really want some standard sources, the Fermilab website has good information, educational material. Then the CERN website has good material. There are also now very many good biographies. Of course, there's the Genius, which is the biography of Richard Feynman. Then there's a book called Strange Beauty, which is a biography of Murray Gell-Mann. Then I have at least one biography of Oppenheimer, which is enormous. It's about 1,000 pages. I don't know who had the patience to write. It's an amazing book. There's also a very good biography of Hans Bethe. You can have a look at that. As far as Indian scientists are concerned, this is very poorly documented. It is very disappointing that we don't have any decent biographies of most of our scientists. Only Raman, there are a few decent biographies, very few and far between. There's also recently, we've been hearing about Bibha Chaudhary, I hope I got the name right, was a cosmic ray pioneer. Now people have begun to write about her and to read about her.
So Indian scientists are really very poorly represented in the world of biography, and I think there's a lot of work waiting to be done. Somebody has to take up all these things and do a good job of this.
We are running short of time, so I'll take the last question. And people who have put their questions up and have not been answered, please don't be disappointed. You may post it to us, and we'll try and answer you, as much as we can. So the last question is by Anushka. Coming from engineering background, what were your challenges in the field of science? I'm asking because I also come from engineering background.
I come from an era when we had many decent courses already. Mine was the last 5-year batch in IIT Madras. So that meant the first 2 years were all maths, physics, and chemistry courses, and a few other engineering courses. So to some extent, I would say that I was fortunate that I almost did a parallel BSc along with a BTech course. The challenges are, of course, there, but there are challenges everywhere. If your foundations are good, you have the perseverance to do good structured coursework, and you are very sincere about coursework, then I think that you can overcome all these challenges. The general tendency in the modern world is to view coursework and all as a nuisance, and people want to write their first paper in Nature and Science by the next weekend. It doesn't really work like that. For some people it may work, but in the long term, it's very important to have your fundamentals right and to really chase truth. So that is, I think, the crucial thing.
Okay, I think with this we can end today's session. This was a very apt and very true to the intention of Paraspar, and we thank Professor Ananthanarayan for his wonderful lecture. We have learned a lot. We have really got a very good insight of the kind of research you have been doing or you have been in the field of. Thank you so much. And the next lecture will be on 10th August. We'll send out the announcement in IISc website. We hope that we'll get the same kind of participation. Today there was 100 participants, and we could not add more. So we apologize for that. And thank you, everyone. Thank you so much. Thank you, Professor.
Thank you for having me. Thank you.
Thank you.